Türkiye döküm sektörünün değerli temsilcileri, kısa bir problem oldu. Onu aştığımızı varsayıyorum. E, TÜDOKSAT Akademi'nin düzenlediği webinarlar serisine hoş geldiniz. E, evet, COVID-19 koşulları nedeniyle webinarlarımıza devam ediyoruz. Gönül arzu eder ki seminerler olsun, yüz yüze sohbet edebilelim ama bunun şu günlerde mümkün olmadığını hepimiz biliyoruz. Daha ne kadar devam edeceğini de bilemiyoruz maalesef. Bizim bir önceki webinarımız 10 Ağustos'taydı. Bu ASK tarafından maça boyalarının seçim ve uygulama kriterleri konusu anlatılmıştı. Hakan Kakaç tarafından. Bir sonraki webinarımız da 7 Eylül'de. Bu DİZA'dan, Metemak DİZA'dan yaş kum kalıplamanın bugünü ve yarını konulu bir sunuş olacak. Perlersen sunacak bunu. Bugün ise ekspertin temsilciliğini yaptığı Elkem'den Çelik Dökümde Tane İnceltici kullanım ve avantajları konusunda Mr. Mauset, Norveç'ten kendisi bize sunum yapacak. Her zamanki kurallarımızı hatırlatıyorum. Sohbet kutusuna sorularımızı yazıyoruz. İngilizce veya Türkçe olabilir, fark etmez. Biz sonuç sonunda Mr. Mauset'e soracağız sorularımızı. Webinar sonunda düzenlenen ankete mutlaka cevap verin. Oradaki görüşleriniz bizim için önemli. Bunları değerlendiriyoruz. Onun dışında webinar boyunca eğer ihtiyaç duyulursa ekspertten Gürolan Bey ve Arif Bey bize açıklamalarda bulunacaklar ama sunumun yarı İngilizce, yarı Türkçe olduğunu bütün sunum sayfalarında göreceksiniz siz de. Sunum İngilizce olacak ancak slaytlar iki dilli olacak. Webinarın kaydı tutuluyor. Bu kayda TÜDOKSAT Akademi web sitesinden ulaşabilirsiniz. Bu sunum formatında sizlerle paylaşılmayacak. Webinar formatında, video kaydı formatında paylaşılacak. Orada görebileceksiniz. Keyifli bir anlatım olmasını diliyorum. Mr. Mauset, first, could you introduce yourself and then start presentation for the webinar? Thank you.
Thank you. Thank you. Yes, thank you for the possibility of having this webinar and showing off our grain refiners. First, I can say a little bit about myself. My name is Håkon Mauset. I have a Master of Science in Material Science and Engineering, focusing on physical metallurgy. And at the moment, I'm also doing the education for the IWE, International Welding Engineer, to be completed in January 2022. Of relevant work experience, I used to work at a company which was called Scana Steel Stavanger and then Nomac from 2011 to 2016. It was a stainless steel mill and foundry. I used to work there as a process developer and then technical manager and chief metallurgist. The foundry there had 2 EAFs and 1 AOD converter. In the forging shop, there was focus on stainless steel, duplex, super duplex, and nickel-based alloys. And in the foundry, we focused on carbon steels, alloyed steels, stainless, duplex, and manganese steel. It had a range of 500 kilograms to 20-ton casting weight. So this has been my main foundry and steel mill experience, as I was responsible for all of the technical follow-up in the whole production. And then I worked a couple of years in a smaller company called Resitec, where I worked as a process engineer and metallurgist, looking at separation technology, minerals processing, industrial byproducts, and circular economy. And then from 2019 and onwards, I work as a segment manager for stainless steel in Elkem. And that means I focus on specialty ferrosilicon for stainless steel mills and EGR, Elkem grain refiner, for foundries and steel mills. So then I think we can just start to look at the agenda. We've had an introduction now first from TÜDOKSAT. Then the first part now will be on the introduction to grain refining of steel with the Elkem grain refiner alloys. So some fundamentals. Then we will go into case studies. First, we will look into the austenitic and duplex stainless steels. Then we will look at manganese steel or wear-resistant manganese steels. And then the final part will be on high chromium white iron and heat-resistant stainless steel. And finally, there will be some times for questions and hopefully answers as well. So, first of all, introduction to grain refining of steel with the Elkem grain refiner alloys. First of all, what do you think are the benefits of grain refinement of steel? Well, what we know theoretically and also from practice is that you get increased strength and toughness. You should get better castability, reduced porosity, reduced hot cracking, and reduced segregation. Why should we grain refine steels? Well, when we grain refine steels, then we can, for example, look at the mechanical properties and the Hall-Petch relation. And this is the Hall-Petch relation, and it clearly shows us that the smaller the grains, the stronger the material. So when we see this from the curve here, that the smaller the grain size, the higher the yield strength. So we actually see that by playing with the microstructure, the grain size, we get better mechanical properties. And also the nice thing about grain refining is that you don't only get strength, you also get better toughness during grain refining. So, but how does a grain refiner function? Well, what we believe, and you see a lot in the articles and theory, is that a grain refiner introduces particles or inclusions into the steel, which then should give a finer solidification structure, which also should give better castability, and should get a finer final microstructure for better mechanical properties. So essentially, you should create active inclusions in the molten steel. This will modify the microstructure, both during solidification and finally, and this should improve the mechanical properties. But what are the requirements for a grain refiner? You need to have thermodynamic stable particles. It doesn't help you if your particle dissolves in the steel. It needs to be a thermodynamic stable solid particle. I'll just get this up. And then there needs to be a low misfit between the formed inclusion and the solidifying metal. And this can perhaps be a bit difficult to interpret. In this figure here, the upper right figure, we have degree of undercooling here on the y-axis, and then the degree of misfit here at the x-axis. And essentially, when we speak about misfit, you have to think that these inclusions or these particles that we will use for grain refining, they are various, they can be various oxides or sulfides or oxysulfides. And the, let's say the lattice structure of the particle needs to fit well with the solidifying steel. So if we look at this figure here, we see that, for example, manganese oxide, MnO, is up here at the far right corner. So we see that it has a very high misfit between the solidifying steel lattice and the MnO matrix, and you would need a very high degree of undercooling in order for the MnO particles to be a nucleus for the steel. While if you look at this one down here, which has a very low misfit, it requires very low undercooling, then we are at cerium sulfide. And we also see here, for example, that in general, rare earth oxides require very low undercooling and have a very low misfit. So, and if we look at the figure here on the right, it shows the misfit between austenitic manganese steel and titanium nitride, cerium oxides, and cerium aluminates at increasing temperature. So here we have on the y-axis, we have the lattice dysregistry or the degree of misfit. And then we have here at the x-axis, we have the temperature in Kelvin. So for the manganese steels, the wear-resistant manganese steels, the old-fashioned grain refining has been to add ferrotitanium to promote titanium nitrides, titanium carbides, and titanium carbonitrides. Well, what we actually see is that titanium nitride has a quite high degree of misfit between the austenite matrix and the titanium nitride itself. And it's increasing with increasing temperature. So essentially, it will take a lot of undercooling for titanium nitride to be able to be a nucleus for the solidifying steel. While a cerium oxide or even cerium aluminates should be far better as a nucleus, because they have a very low dysregistry, and it's even decreasing as the temperature is increasing. And we also see that cerium oxysulfides have a quite good dysregistry. So, but then the concept of misfit, as I said, it can be a bit difficult to understand, but if you look at these simple spheres here, see these spheres, they have the same diameter, all of them. And we see that here we have one row, and then the next row fits excellent in the voids here. And we have a repeating pattern. So here we have a low misfit. These spheres, they fit good together. And here we have an example of high misfit. Here you see it then, these spheres, they have a different diameter than these ones. And we see that this row of spheres do not fit well with this row. We see we don't get the repeating pattern. There is a difference in the voids between them. So, but this is also an example of low misfit. We don't need to have particles that are exactly the same like we have here. Here we have particles with one diameter, and here we have particles which has a diameter which is a multiple of this diameter. So then we see that these fit quite well again. We have a repeating pattern. You see the same size and shape of the void between them. So how do we obtain the proper inclusions to get grain refining? Well, we could do like you do in aluminium by adding the specific inclusions you need. For example, titanium borides in aluminium. Or we can choose another way, and that is what we have done in Elkem. We do it by alloying. So the actual inclusion is a reaction product from the alloy that we put into the steel. So typically it is a strong deoxidizer or desulfurizer like cerium or lanthanum, zirconium, and other elements, reactive elements that you can put into steel. And by using this principle, we have designed two types of grain refiners. We have the EGR wear seed and the EGR stain seed. And then we will come back to them. So just for a small repetition, the function of a grain refiner is to create active nucleation sites for the solidifying steel. This improves the microstructure. And by improving the microstructure, we get increased mechanical properties. So then we go into the actual grain refining alloys that we have in Elkem. That is the EGR wear seed and the EGR stain seed. And the active elements in both of these alloys is cerium. And the grain refiner, the alloy is added to liquid steel. And then the cerium, it will react with the dissolved oxygen and sulfur in your steel, and it will form stable particles evenly distributed in the melt. So depending on the amount of oxygen and sulfur in your steel, you will create cerium oxides, cerium sulfides, or even cerium oxysulfides. And of course, if you have some dissolved aluminium as well, you can get cerium aluminates in there. And all of these are suitable particles to promote heterogeneous nucleation and get grain refining in your steel. So, as I said, all these particles work as heterogeneous nucleation points during solidification. So here we have the two alloys. First of all, we have the stain seed, which is meant to be used for stainless steels. It has the nominal chemistry is about 10% of cerium, 20% silicon, 30% chromium, and then less than 0.15% carbon, as most of the stainless steels are very low in carbon. And then iron makes up the balance. The wear seed is designed for manganese steel. So here we have quite similar, 10% cerium, 24% silicon. Then we have 10% chromium, as a lot of the manganese steel contains some amount of chromium. We have 24% manganese, and then the carbon is less than 1%, which should be okay, as most of these manganese steels contain more than 1% carbon anyways. And then iron is the balance of this alloy as well. The standard sizes that we have for both of these alloys are 2 to 20 millimeter, and then 0.2 to 2 millimeter. But it can also be delivered as cord wire on request. And as I mentioned, the chemistry for both of these alloys mentioned here is the nominal composition. So here you have, this is the first page of the data sheet for the stain seed grain refiner that can be obtained by contacting expert. So I will not go too much into this. As I said, this is just the first page, describing the alloy and showing some applications. We of course have the same for wear seed. So, and both of these can be obtained from expert. So then we will look a little bit into how do we actually add EGR during the production of steel. Well, the addition rate of EGR wear seed and stain seed is normally 6 to 7 kilograms per ton of steel. What we aim for is approximately 0.04 weight percent of cerium, or 400 ppm of cerium in the steel. And the way we add the EGR into the steel is very important to do correctly. Typically, the addition of EGR is something you do just before casting. So typically here you have your induction furnace, your electric arc furnace, or your AOD converter, and you start to tap steel into your ladle. So here we have the ladle. Usually you should try to fill it up about 1/3 with steel. And then you should start to add the EGR wear seed or stain seed. And yeah, the alloy should be packed in bags, paper bags or plastic bags, between 5 to 10 kilograms in each bag. And then you should try to add it as evenly as possible between 1/3 and 2/3 filled ladle. So you have to distribute the EGR during the filling. And it's also very important where you actually hit with the EGR. You should not hit directly into the tapping stream, because then it can just bounce off. You should not hit close to the ladle wall, because then the material can just stick to the ladle wall. The bullseye is here, as close as possible to where the tapping stream is hitting the metal in the ladle, because then the alloy will be dragged down into the steel, and it will dissolve before it manages to float up again. So the way this addition is done is very important, and we immediately see it with regards to the recovery of the cerium. If this is not done in a proper way, then you get very little cerium into the steel. A lot of it is just slag on top of your steel, and it does no grain refining at all. So, and if you are really good at how you're doing this, you can obtain up to 70% recovery of the cerium. So, but one important thing to look through before doing any trials, and that should be discussed with us, is of course the deoxidation practice that the foundry has. because the choice of the oxidant and the method of addition of the deoxidant needs to be considered before you start using EGR. So if you're adding, for example, aluminium or calcium silicon into the ladle, there needs to be discussions on how to do that properly before we start to add EGR. So then we are actually finished with the general introduction to EGR. Now we will go more into the case studies. And then we will start off with the austenitic and the duplex stainless steels, and also super duplex. So, what do we think that we theoretically can achieve by grain refining of stainless steels? Well, we expect to get a smaller grain size. We should have less segregation in our casting. This should give us better mechanical properties. Should give us less casting defects, and we should also get less weld repair on the castings. This first case here is not from a foundry. This is from a steel mill producing ingots. This is the steel grade called 254 SMO. You see, it's a very highly alloyed super austenitic steel. The 20% chromium, yeah, less than 1% copper, 6% molybdenum, and then around 18% nickel. Also, you see a lot of nitrogen. So it's a really highly alloyed steel, and usually segregates a lot during solidification. So, but for this specific trial, then a 5-ton ingot was cast. You can see it's about 2 meters high and 540 millimeters here on top. So what they did was that they 1/4 from the top, they cut out a slice, and then they took out this test sample here from that slice. So here you have the surface, and here you have the middle. So 70 millimeters from the surface of the ingot. Well, before this steel mill used mish metal for grain refinement of this alloy. So and mish metal is of course a mixture of cerium and lanthanum. And this is how the microstructure looked like 70 millimeters from the surface. So quite coarse grained. While here you have the results after they used Elkem grain refiner with just cerium. So you can see there is a big difference in the microstructure here. So a much finer dendritic structure when they replaced mish metal with EGR stain seed. So this is the test bar that I showed you earlier. So here we have, this is the surface of the ingot, and now we're looking 70 millimeters from the surface. If we then go into the center of the ingot, then we see it's an even more coarse structure when they used mish metal. And here you can see it's much finer with the EGR stain seed. And what they actually saw was that normally this steel mill, they had a lot of problems when they were forging these ingots into bars. They got a lot of cracking during forging, and they had to do a lot of grinding of the ingot and also the forged bars. So it took a lot of time, and they lost a lot of money when producing these grades. But when they started to use the EGR stain seed, they had no problems anymore with cracking during forging. Then the next trial was 254 SMO castings at a foundry. So, and they had problems achieving the mechanical properties for these castings. Both impact strength and also the tensile strength was a problem. And they had problems with the surface. They had to do a lot of weld repair on these castings. I think it was valve bodies. So, but when they started to use EGR stain seed, the sharp impact properties went up more than 65%. and they saw less variation between the single values. As you all know, during Sharpie testing, you have 3 samples that you test, but the variation between each of these samples was very, very little when they started to use EGR stain seed. With regards to tensile strength, when they didn't use EGR, they had problems to meet the minimum value of 550 megapascals. But with EGR, they typically achieved 590 megapascals, so more than 7% above the minimum requirement. The yield strength, they had a problem to meet the requirement of 260 megapascals, but with EGR, they achieved 290 megapascals, so 11.5% above the minimum requirement. And as I mentioned, they had a lot of surface defects, which they needed to grind and weld on, but the problem disappeared when they started to use EGR. So I think they didn't have any weld repair connected to the surface anymore. So this is not the exact component, but this is a typical valve body. Then we go into the duplex deals. This is a 22 chromium duplex, so 22 chromium, 5 nickel, 3% moly. This is a forged material. So these are not the best pictures, but at least here you see this was the normal structure they had in their forged components. And then with the Elkem, when they started to use the Elkem grain refiner, this is how it looked like. So we see that the spacing between the ferrite grains is much more narrow when they started to use the Elkem grain refiner. So there is a definite grain refining here. Then we have the 4A duplex, which is the 22 chromium duplex, but in cast version. So here we have, this is not a customer. This is the reference casting, how their duplex structure looked like without any EGR in it. And this is how it looked like when they added EGR. So you can see it's lots smaller ferrite grains here. So here we have, this is also the 4A grade. Here we have the reference here. You can see that we have a quite big columnar zone, quite coarse columnar grains. And then we have this equax zone here, where we see the grain size of the equax grains. And this was without EGR. But then when they start to use stain seed, you can see there is more, very little columnar zone. And we can see that the equax grains are much smaller. So the actual grain size in the equax zone was 1.75 millimeters. And when they started to use stain seed, the equax zone was the grain size in the equax zone was 1.3 millimeters. So there was a reduction of 25%. So we're still at the 4A duplex grade mechanical properties. We will not dive too much into all of these numbers, but we typically see that for the yield strength, the reference was for 477 megapascals. They achieved 511 megapascals. So that's 7.1% in change. For tensile, see the same, went up from 726 to 752. That's 3.6% change. And then perhaps the most important is the Sharpie values. You can see here that there is quite a lot of deviation between the 3 samples here. The average is about 132 joules. But if you look at the one with EGR, there is much less variation between the single values. And then we're at 145 joules. So an increase of 9.8%. So, and this one you see here in these figures as well. that there is an increase in both yield and tensile strength when EGR is added. And yeah, for these grades, the most important is of course the impact strength. So you can see here that the reference, this is the average, but there is a big spread between the values. Well, here we have an overall better average and much less spread. Then we go into, this is a forged steel. This is a super duplex called 1.4501. Super duplex stainless. It is the super duplex with tungsten and copper. So here we have the reference sample. No cerium at all. So this is the equiax zone, and here we have the columnar zone. While this is the one treated with EGR. Here you see we have 640 ppm of cerium in the steel, and there is really no visible columnar zone here, and it's a lot more. The equiaxed grains are much smaller than this one. So other benefits we've seen with EGR in duplex is better weldability and less repair welding on the castings. So then we go into the wear-resistant manganese steels. So what can we theoretically achieve by grain refining of manganese steel? Well, we think that we can achieve a smaller grain size, less segregation, better mechanical properties. And we think that these better mechanical properties, they should lead to increased lifetime of the crusher components. We should get less casting defects. And we also think that by having a better solidification, we should have an increased casting yield, and thus it should be possible to reduce the feeder size. This one we have not worked on yet, we have not documented it yet, but it is something we are looking into. And of course, if you have a smaller grain size, then perhaps you could reduce the heat treatment time of these components. So first we have the microstructure and average grain size in a steel with 17% manganese. This is the reference casting. You see the average grain size is 167 micrometers. With EGR, there was a 15% reduction in size. So the average is about 145 micrometers. So, and we increased the impact strength in this grade without any loss of tensile strength. So we went from 100 joules on the Sharpie testing up to 130 joules. So that is quite substantial. And the tensile strength stayed at 880 megapascals. Then we can look a bit at a 12% manganese steel with EGR. So for this one, we see what we have seen earlier, the Sharpie impact strength at 20 degrees C. Typically around 35 joules without EGR, but then up at 60 joules with EGR. And we see sort of the same here, a bit lower here with EGR. When we look at the tensile strength, we see that without EGR, we are at 780, 800 megapascals. But with EGR, we are more up at 840 to 860 megapascals. And we also see that the elongation after fracture, the A5, increases as well. We're typically at around 20% elongation without EGR, and at 25% with EGR. So we see here the impact strength is up 50% without any loss of tensile strength. So we actually see here that we get both increased tensile yield strength and tensile strength, but we also improve the ductility and the toughness of the material. So, and that's quite rare when you work with steels. Usually you have to choose better strength or better toughness, but here we actually get both, which is in line with theory, of course. Then we have a case with a 20% manganese steel. And this is the reference sample. You see the scale bar here is 500 micrometers. And you see these grains are huge. And the normal practice for this foundry was to add 0.1% aluminium and 0.4% titanium to the ladle just before casting. And then we did some trials where we kept the aluminium, but we skipped titanium, and then we added 0.7% of EGR instead. And then you can see that the grain size, it's substantially smaller. So here we have a really big effect of the EGR. So, well, then again, usually for these manganese steels, the foundries are not really interested in mechanical properties because the end user is going to use them to crush rocks, and then all they're interested in is the actual lifetime of the components. And of course, smaller grain size should lead to better mechanical properties, which then should lead to a better lifetime for these components. So, but this was the first trial where we actually saw an increase in the lifetime. So this was shredder hammers that were made in a manganese steel, around 13% manganese. This is the reference casting. You see here, this red line here is 1 millimeter in length. So it's quite coarse grained. And then when they started using EGR, you see here, this red line here is still 1 millimeter, but you have much smaller grains. And what this foundry saw, or the customer of the foundry saw, was they achieved a 25% improvement in lifetime of the hammers when they started to use EGR. But then again, for these manganese steels, we saw that we needed to have more actual lifetime data. And the thing is that at Elkem, we have a lot of crushers around the world. And especially in the northern part of Norway, we have Elkem Tane, which is a big quartzite mine. And they have a huge jaw crusher and a huge cone crusher. So we decided to do some trials internally in Elkem. So then we chose to make a manganese steel of 1.4% carbon, 2.5% chromium, and 20% manganese. And then we added 6 kilograms per ton of steel. We added EGR wear seed. And from this steel melt, we made the inner and the outer mantle of the secondary cone crusher at Elkem Tane. The total casting weight of these two components was approximately 5 tons casting weight. And these mantles were put in operation at Tane some time ago, and then they measured it. They have a continuous measurement of all the mantles they put into their cone crusher. So, and then they saw that these EGR treated mantles, they had an increase in lifetime of more than 50% compared to the average lifetime for the last 10 years. And actually, when we compared it to the last 3 years, then it was actually 100% increase in lifetime for these mantles. So that is, of course, very good numbers. And so the mine decided to order a second set of these EGR treated mantles, and they will be put into operation quite soon. And we hope, of course, that we get similar numbers or even better. And hopefully we will do several trials up there to see that we get the same effect. And in addition, they have also ordered plates for their jaw crusher. And these are quite big plates. They're around 2 to 3 tons per plate. And they will be put into operation quite soon as well. From these trials, we have made test blocks, both with and without EGR for comparison of microstructure, but these have not been finished with regards to characterization. So hopefully at the later webinar, we will be able to show the microstructure from these. And we have also obtained a piece from this actual mantle after it was finished used. So we can look at the microstructure in the actual casting itself. And based on these good results, we have started to have discussions with other Elkem plants as well, especially the ferrosilicon plants and the silicon plants, where we have a lot of cone crushers and jaw crushers and even roller crushers. So during the next year, we will probably do trials at several of the Elkem plants, both in Norway and in other parts of the world. So that's going to be very interesting to see the results from these trials. So this is a bit of a side story. This is not wear-resistant manganese steel for mining applications. This is TWIP steel, which is typically 20 to 24% manganese, but they are continuously cast and there are advanced high-strength steels. So this is the reference casting from a continuous casting machine. No cerium addition here. And this is the side of the as-cast slab. And here we see really coarse-grained columnar zone. And we see this typical cross here. And this is the center of the slab. Here you still see there's really large grains, columnar grains. But then a trial was done with EGR. You can see that we have around 700 to 800 ppm of cerium. Here we have the side of the slab. So see, it's much more fine-grained. You don't see these columnar grains at all. And same here at the center of the slab. It is much more fine-grained, which should make it easier to hot roll later on. And hopefully it will be less susceptible to cracking during casting. So then we're moving into the last part here. So we're running a bit fast through it. Now we will speak a bit about high chromium white iron and also heat-resistant stainless steel. So what do we expect when we grain refine high chromium white iron and heat-resistant stainless steel? Well, as we've said numerous times during this presentation, we expect to have smaller grains. We also expect to have smaller carbides, and we expect that these will be well-dispersed carbides. And of course, we expect to have less segregation. Okay, that's double one. Okay, first, high chromium white iron. Here we only have, so far have one case study we can show off. This is a high chromium cast iron for rolls used in a steel rolling mill. The nominal chemistry of this grade was 3% carbon, 17% chrome, 1.5 nickel and 1% moly. And then EGR stain seed was added with 6 kilograms per ton of molten metal. And here you see the microstructure. This is the microstructure in the castings without EGR, and this is the one with EGR. So what the customer saw was more and smaller EQX grains and smaller and more well-dispersed carbides. So we saw everything we wanted to see in these high chromium white irons. So, and this is of course a very interesting thing for us to look into, because Elkem has been very good when it comes to the gray cast irons and the ductile cast irons, where our inoculants promote graphite. But of course, the white cast irons we haven't really worked much on. So, but we see now that there is an effect of EGR in these grades, and we will be working hard to do more trials at various foundries. So to look more into the effect. Then we go into the heat-resistant stainless steels. So this is from a customer. They use the EGR stain seed 2 to 20 millimeter, and they add 0.7%, so 7 kilograms per ton of steel. What we see here is cooler plates, and they make these in the ASTM A297, the HH grade, the HK, and the HD grade. So typically the chemistry we see here is the 24% chromium, 11% nickel, and 0.4% carbon. So of course these stainless grades are really high in carbon compared to other stainless grades. So, but what this customer sees is that the casting life is increased, or the lifetime of the components when they are put into operation. Typically this can be used put in cement production. So the lifetime of the component has increased. The heat resistance properties are improved. They avoid columnar growth. They see a smaller grain size. And actually this customer, they give a much longer warranty on the castings that are produced with EGR than the ones without EGR. Then we go into the exhaust manifolds and turbos. And of course, these heat-resistant stainless grades, they were originally made for industrial applications, like you saw cement plants and steel mills and everywhere where you have high temperature applications. So, and exhaust manifolds and turbos have traditionally been made in cast iron. But now we see in the industry that the exhaust gas temperatures from the engines, they have a steady increase as we are getting smaller engines with more turbos. So as the temperature is increasing, a lot of the manufacturers have to switch to heat-resistant stainless steel. So, and therefore, of course, it is interesting for Elkem to look into these exhaust manifolds and turbos and see if they are suitable candidates for grain refining with EGR stain seed. Of course, if you look at the typical industrial castings that these grades were made for earlier, they are quite large and thick components, while the manifolds and turbos usually are quite thin-walled. So there is a definite difference there. So, but the typical grades used by the automotive industry, they are in the ASTM A297, but with some modifications. It is typically the HF, the HH, the HK, and the HU grade that they use. But often they add some niobium in there as well to get some extra carbides. I don't have anything to show off at the moment. We have industrial trials are under planning in several countries worldwide. We started before COVID, but then COVID came and made a lot of these activities more difficult. But we are performing small-scale trials at a European university, and we are expecting to have data during autumn now in 2021. So that'll be very interesting for us to see how the EGR works. At the moment, we're focusing on this HU grade, which is around 38 to 40% nickel. So it's very, very different from these other grades. Then we have the grade of 253 MA. And the heat-resistant stainless grade 253 MA is one of very few steel grades which actually has a mandatory cerium content. And you see the composition here. It is a grade that was invented by Outokumpu Avesta many years ago. And it's probably the stainless or the heat-resistant grade that can handle the highest service temperature I think it's around 1150 or something, 1150 degrees C, and is also very good for cycling between low and high temperatures. So, what you see here at it, the nominal composition is 500 ppm of cerium. So, but our EGR stain seed is supplied by both steel mills and foundries for alloying with cerium instead of using mish metal. I think a lot of the steel mills and foundries that make these grades, they use mish metal, and then they get a lot of lanthanum as well. But we have several customers who use our stain seed as a cerium alloying agent, not for grain refining, but for cerium alloying. And one of the reasons is that our stain seed has a cerium recovery of up to 70% of the cerium, while mish metal cerium recovery usually is much lower. I don't have any specific numbers myself, but I've heard 10 to 30% recovery. And of course, also mish metal is very reactive when you put it into steel. There is a lot of light and smoke and such, while adding EGR stain seed, nothing is happening. There is no reactivity. So that was it. We are finished a bit earlier than anticipated, which means we have more time for questions and answers. The contact info you can see here in Turkey. Then Expert is our distributor. So therefore it is best if you contact Arif or Gulan at Expert. But also we have here my contact info. So
thank you, Mr. Mauset. Thank you. It's a very informative presentation, and hopefully steel makers will get lots of benefit from this presentation, because the targets are quite impressive, increasing not only the strength but also the sharpie notch strength and the elongation, quite satisfactory results. And that's very good for the results that you have shared with us. Are you able to see the chat box, Mr. Mauset?
Let me see here.
If not, you can close the presentation and we can look at the chat box together.
Mm-hmm. It's good. So I can see the chat box, but probably you cannot see it. I can stop.
Ooh, yeah. The chat box is there. There's a question there.
Mm-hmm.
The chat box.
Do you want me to show the chat box, or should I just read
it? No. Just read it. From Talha Çakmak. He's saying that, hello, thank you for this impressive presentation. I got 2 questions. Can we choose grain refinement additions according to our composition, according to changes in SFE values? What is the relationship SFE on a system between big misfit grain refiner?
SFE values. I must admit I don't know exactly what he's pointing at.
Let us Tunçer Bey açabilir misiniz? Arif Bey'in ve Gürolan Bey'in mikrofonlarını.
Benim mikrofonum açık.
Tamam, güzel. Gürolan Bey, siz SFE'nin anlamın konusunda bir şey biliyor musunuz veya sorana soralım?
Bence soruya sorana soralım, çünkü ben de anlayamadım ne olduğunu.
Peki Talha Bey'in SFE'nin açılımını yazmasını isteyelim. Neyin kısaltmasıdır SFE? Onu yazarsa daha bir anlam kazanacak soru. Stacking fault energy.
Stacking fault energy, okay.
Yeah, stacking fault energy. Teşekkürler Talha Bey. Mm-hmm.
Well, I must admit, we haven't really looked into stacking fault energy. We have not gone that deep into it. But of course, I would assume that would assume that, of course, if you have a better solidification, you might reduce the stacking fault energy. But no, I must admit we have not gone that deep into it yet. We are looking into similar things, but not at the moment. We don't have any data on this.
Okay.
Tercümeye gerek yok sanırım. Soruyu soran İngilizce sorduğu için diye
Tabii,
düşünüyorum.
tercümeye gerek yok. İngilizce soran sorduğu için cevabı da İngilizce olarak almıştır. Bu konuda çalışma yapılmadığını bildiriyor kendileri.
Yani bildiğim kadarıyla bu tane sınırlarında hatalı enerji birikimiyle ilgili bir durum. Ama tabii Mr. Mauset bununla ilgili herhalde bir şey yapacaktır. Daha sonra bir çalışma yapacaktır.
Evet. I have got a question, Mr. Mauset. You have indicated that those grain refiners have got two sizes. One is 0.2 to 2 millimeter. The other one is 2 to 20 millimeters.
Mm-hmm.
So what is the reference that which one is for which purpose?
We usually look at the size of the ladle that the foundries use. So if you typically have ladles that are like 1 ton or 2 to 3 tons, then it could be wise to use the smaller edition, the 0.2 to 2 millimeter. Well, if you have a bigger ladle size, like say 5 or 6 tons or bigger, then the 2 to 20 millimeter size is better. So.
Thank you. Tercüme etmeye gerek var mı Arif Bey? İster misiniz tercüme etmeyi?
Biz şey yapalım isterseniz.
Tabii.
2 ayrı tane inceliğinde piyasaya sunulan bir ürün. 3 tona kadar daha ince tane. 5 ton ve üzerinde de 2-20 milimetre tane boyutu kullanılıyor. Biz yoğun olarak şu anda manganlı çelikler için özellikle 2.20'yi çok uzun süredir aktaş döküme sağlıyoruz. Yani bu Türkiye'de hiç denenmemiş bir ürün değil. Çok uzun yıllardır manganlı çelik üretiminde aktaş döküm kullanıyor bu ürünleri.
Şimdi Gürolan Bey, başka soru yok. Arzu ederseniz şey yapalım. Bu sunumla ilgili ilave görüşlerinizi paylaşırsanız katılımcılarla daha keyifli olur diye düşünüyorum ben.
Biz açıkçası 2017 yılından beri bu Elkem'in bu ürünüyle ilgili saha çalışmaları yapıyoruz. Türkiye'de özellikle paslanmaz çelik, dubleks ve süper dubleks ve mangan çelikle ilgili giderek artan bir üretim şeyi var, miktarı var. Dolayısıyla da bu konuda çalışma yapmak isteyen herkesle de saha çalışması el verdiği kadar yapabiliyoruz. Daha ayrıntılı da bize ulaşırlarsa sorulara da cevap verebiliriz.
Ben de şunu ilave etmek isterim. Açıkçası dökümhaneler, yani çelik dökümhaneleri bu ürünle ilgili çalışma yaptıklarında bu kendi içlerinde de iyi bir Ar-Ge çalışması olur diye düşünüyorum. Çünkü direkt bu mekanik özellikleri ve o parçanın ömrüyle ilgili iyi sonuçlar veriyor.
So, Mr. Mauset, there isn't another questions for this presentation. I believe that everybody got the message quite clearly. So could you want to say last words about this possibility to use Elkem grain refiners?
Yeah, I can say actually a couple of things. Of course, as you see in the presentation, we have focused mainly on stainless steels and manganese steels, so the austenitic steels and duplex steels. We have not worked much on the ferritic steels, but of course, for a lot of foundries, it can be interesting with the carbon steels and the low alloyed steels, and those we are working on now, especially here in our R&D facilities. So we have some very promising results on carbon steels as well. We cannot show them now, unfortunately, but if anyone is interested to discuss more on the carbon steels as well, we are interested to discuss with them.
Tercüme etmek gerekecekse manganlı çelikler ve paslanmaz çeliklerle ilgili bu zamana kadar çalışmalar yapmıştık ama karbon çelikleriyle ve düşük alaşımlı çeliklerle ilgili de çalışmalarımız devam ediyor. Bunlarla ilgili de çok kısa bir süre içerisinde sunum yapacağız.
Mr. Mauset, thank you very much for your kind presentation, very informative presentation, and hope to see you sometime in Turkey, possibly after COVID-19 case, let me say. The first chance could be next year in June, on 8th to 10th of November. There is Ankiros, and together with Ankiros, there will be Turkish Founderman Association's International Founder Congress there, and hope to see you there and your colleagues as well. Thank you very much. Have a nice day.
Thank you very much as well.
Değerli katılımcılar, bugünkü sunumumuz burada sona eriyor. Katılımınız, gösterdiğiniz ilgi için teşekkür ederiz. Hepinize sağlıklı, COVID-19'suz günler dileriz. Hoşça kalın.
Teşekkür ediyoruz katılımlarınız için.
Teşekkür ederiz.
Sağ olun.